Okay, so in this lesson, we're going to be looking at velocity and some other rates of change. This is the first part. So in this lesson, we're going to start exploring some applications for the derivative of a function. So as we look at real-life problems, it's important to remember the phrase rate of change means the instantaneous rate of change, which is the derivative of a function at a specific point. Okay? How do we interpret the meaning of a derivative in context? A derivative, f prime of x, gives a rate of change of a function, f of x, at one particular instant in time. To interpret the value of f prime of x, you must include the big 4, which is context of the function, the rate of change, the instant that it occurred, so whatever the x value is that they gave you, and then your units. There's a sentence frame that we're going to use to help us write this out. Okay, and it'll make more sense as we do an example to show you. So at x equals, this is that in the instant, so when x equals this value, and then the context of the function, and the derivative tells me if a function is increasing or decreasing at a particular rate. Okay, so this would be the value of the derivative, and this is the units of the derivative. So this is the context of the story, increasing or decreasing. So it's usually if the derivative is positive, this function is increasing. If it's negative, the function is decreasing. So when the derivative is positive, the function is increasing. When the derivative is negative, the function is decreasing at a particular rate. How do we determine the units? Okay, so whatever your function is, f of x, has a particular unit. And so the units of f prime of x are the units of f of x, whatever that is, with respect to x, whatever the units are for x. Sometimes it's time, sometimes it's something else. Okay, so it is the units of the function over the units of x, whatever those may be. Very, very important to remember your units. It actually counts at certain points on the AP exam. So here's an example I'll lay out for you. Let me scroll down here so you can see it. So the function j of t is the number of jelly beans in a bowl after t hours. Okay? The number of jelly beans, the number of hours is t. This is a graph of j of t. So what are the units of j prime of t? Well, j of t is the number of jelly beans, and t, the units of t, is hours. Okay? So what about the second derivative? What would be the units of j double prime of t? Well, the second derivative is the derivative of this function. So what are the units of this function? The units of this function, j prime of t, is this, and then the units of t. So it'll be the number of jelly beans per hour. That's the units of j prime. And then per hour would be the units of rt again. So you can write it this way. You kind of see the separation here. So this is the units of f of j prime and the units of time. You can write it this way, where the units of j prime are on top and the hours on the bottom in like a fraction format. And a lot of times what they'll do is they'll say, because this hour's on the bottom and this hour's on the bottom, I can rewrite this fraction as the number of jelly beans per hours squared. Okay? All of these three mean exactly the same thing. So use the one that you're more comfortable with. Just make sure you use it properly, okay? So let's look at an example of how this is going to be done. So let me pull it down here so you can see the question. So a pie is taken out of the oven. The temperature of the pie in degrees Fahrenheit, t minutes after the pie is removed from the oven, is given by the function p of t. Interpret the meaning of, it's kind of hard to see here, p prime of 10, which is a 10, equals a negative 13. in context. Okay, so what does this mean in context? So I have a place over here we can write. So here's our question right here. So what is p prime of 10 equal to negative 13 mean in context to this story? Okay, so let's go and break down the stuff that we saw up in here. Well, first off, time is in minutes. The temperature is in degrees Fahrenheit. And this function is what we're calling for the temperature of the pie as it's been removed from the oven in degrees Fahrenheit. So P of T is in degrees Fahrenheit. T is in minutes. So what is our units going to be? So what is this going to be? So we need to have our time, which is the 10 at that moment when T is 10. Okay. So based off of our sentence frame, at x equals, and then the context of f of x, so in this case that would be our P of T. So the answer here would be 10 minutes, okay, after the pie is taken out of the oven, the temperature of the pie is what? So this right here is the context of our story, okay? This is when it occurred. This is the context. The pie was taken out of the oven. The temperature of the pie is, and then what is it doing? Well, our number here is negative 13. So because it's negative, I know that the temperature is going to be decreasing. So the temperature of the pie is decreasing at a rate of what? Well, the negative has already been used as the decreasing. So we just use the number 13 degrees. And that would be in Fahrenheit per minute. Because this is a P prime, the degrees of the function, which is the temperature of the pie, per the unit of time. So that's my answer for that one in context, using the sentence frame. Okay? Let's look at the next one down here. Here's the rate at which people enter a water park in hundreds of people per hour. Okay, it is given by the function W of T, where T is measured in hours. Interpret the meaning of this in context. Okay, so what would that be in context? Well, this is our time at that moment in instant at 3. Okay, so we can say at T equals 3 hours. What? Context. Okay, the rate at which people enter the water park is, now we look at what's going on, positive, so it is increasing at a rate of 2.6. The units of the original, this is in units of, in hundreds of people per hour. That's what this WT was given as, right? That was the units of that one. 2.6 hundreds of people per hour, and then the per unit of time for hours, per hour. So remember, you were given this, which was already a rate. It was already a rate. So this is the derivative of a rate. So this is kind of like the second derivative of some function above that. But it is the derivative of this rate. So here's the original rate. And then per hour would be the units of the rate of change. And that would be that one in context. Okay, let's look at another topic that we're going to be doing, the particle. This is one of your big problems. You need to know how to do the particle problem. This is the introductory for it, things you need to remember. Okay, so let's take a look. They use different function names a lot of times, but we have our original function is the position function. Sometimes they'll use x of t if it's going to be a particle on the x-axis only. Sometimes they'll use y of t. They can use any letter they want. These are the most common letters that are used: s, x, and y. They use the y of t if the particle is going up and down the y-axis, x of t if it's on the x-axis, s of t in general. But again, they can use any function name that they want. It is a position. It is measured in units of length, feet, inches, miles, whatever the case may be, meters. Okay. So the next one after we have the position function is we have the velocity function. This is related to how fast something is moving. It tells me a lot more than that though, because velocity tells me it has direction and length. So the velocity function is the derivative of the position function. It is measured in units of length per unit of time, miles per hour, meters per second, and it tells me quite a bit, and you'll see some of the problems and how the velocity does for position. After that, we go to acceleration. This is they use A of t. They always use V of t for velocity, A of t for acceleration. The acceleration is the derivative of the velocity or the second derivative of the position function. And it is measured in units of velocity, so whatever the units of these are, per unit of time. So usually it's meters per second. And again, they can do the little squared underneath it too, but I wanted to see you see it that way. So we're going to explore some of these problems using this. This is the introductory. This one, the particle problem, is not complete until after we've gone through all the material that we need to know. Even through integration, we need to know that to finish off the particle problem. So this is just the derivative side of this. So here's an example. Let me pull that one up. So here we have it right here. A particle's position along the x-axis in meters is given by this equation right here. For t between 0 and 10, t is measured in seconds. Find the particle's velocity at t equals 6. Okay, so this is the position. I'm talking, want to find the velocity. So one of the first things you have to do is you have to find the velocity function. So right out the gate, you want to find the velocity equation off of this position. So you need to take its derivative. When you write this out, please make sure you write it fully and completely. Do not skip. So this is the velocity of t, which is the derivative of s, which is now take the derivative. Please make sure to, oops, I don't know why I put an s there. That is an x. Please make sure you use the right function name. Now take the derivative of this with respect to time. And so I'm going to have the 12, and then chain rule, and the derivative of the sine is the cosine, pi over 6 times t. Okay? Now, once I have that, I want to find the particle's velocity at t equals 6. Well, I have the equation for it. All I have to do now is simply plug it in. What is v of 6? Please make sure you write that down also. So this times that is going to be 2 pi times the cosine. If I put a 6 in here, they're going to reduce out, and I'm left with just pi. Okay? That is the velocity at 6. We just need the units on there. On an AP exam, you can actually stop there. You don't have to continue on. Just make sure you put the proper units at the end over here. But for me, you need to continue on and simplify it if possible, please. The cosine of pi is -1, so this is a negative 2 pi. And then the units would be meters, because that's the measurement for the position, and seconds, because that's the measurement of time. So this is meters per second. And so that would be the solution to this problem. Okay? Now, again, this negative here, and the sign of this thing tells me a lot about the original particle, what it's doing at this moment. Some things you're going to find out. I'll just give you a little heads up here. When this is negative, since the particle is on the x-axis, so the particle is moving right or left. Because it's negative, I know at that moment that the particle is moving to the left, okay, at this rate. So that's one of the things that's useful for the derivative, the velocity. It tells me if it's moving right or left, okay? Let's look at some other information here that we have. Oh, here it is. I just told you, and then I gave it to you. Here we go. Here's the things you need to know, or some of the things you need to know at this point. What information do we get from an object's velocity? An object is at rest when the velocity equals 0, and this is how you start the problem. Set the velocity equal to 0. An object is moving left or down when the velocity is negative. An object is moving up or to the right when the velocity is positive. So when I say right and up, because if I'm on the x-axis, it's right or left. If I'm on the y-axis, it's up and down. How is speed related to the velocity? The speed is equal to the absolute value of the velocity. So in this previous problem over here, when we have the velocity at 6 is a negative 2 pi meters per second, its speed would be the absolute value there, which would be 2 pi. Okay, so think about when you're in the car. Whether you're going forwards or backwards, the velocity, how fast you're going, is not a negative or a positive number. It's always positive. Okay, there's no negative speed. An object is speeding up when the direction of the acceleration matches the direction of the velocity. In other words, the acceleration and the velocity have the same sign. So if you want to find out if the object is speeding up or slowing down at a particular moment, you have to find the acceleration at that moment and the velocity at that moment. And if they are the same sign, then the object is speeding up. If they are different signs, then the object is slowing down. Very important. This is a question that's also on the AP exam. So you want to remember that. Speed is the absolute value of the velocity. An object is speeding up or slowing down based off the sign of the acceleration and the velocity. Same sign, speeding up. Different signs, slowing down. So let's look at another example. Here we go. A particle is moving along the x-axis. The position of the particle in feet can be modeled by that equation right there for t between 0 and 5, where t is measured in minutes. So when is the particle at rest? Let's start with that one. Well, as you saw in the previous thing, the particle is at rest when the velocity is equal to 0. So the first thing we have to do is we have to find the velocity function. So v of t, which is the derivative, the function that they use x again, is the derivative of the position function. And then we take the derivative of this thing right here. This is a 1/3, so 3 times 1/3 is 1. So this is t squared minus 5t plus 4. That is my velocity function. And the particle is at rest when v of t is equal to 0. You want to state that. Okay? You can also do it right here. And you just put equals 0 here. Does the same thing. You want this line to say v of t is 0. Very important. And then after that, we can factor this out, solve this. I still have a 0 equal here because it's still, I need to say that. Here's the t, and then here's the 4 and the 1. Both of them are minus. There it is factored. So we have t equals 4 or t equals 1. Okay? 2 times when the velocity is equal to 0, so 2 times the particle is at rest. And you write your answer. The particle is at rest when t equals 1 minute and when t equals 4 minutes. And there is your solution and everything you need to show me for part A. Well, let's look at part B. This is part A. What is part B one? When is the particle moving to the left? Well, a particle is moving to the left when it is negative. Okay? So one of the things that help us do this, we have our velocity function right here. We don't need to redo it. We have it factored, which makes our life really good. We know when it is 0. These are things you have to do. Okay? So you want to make a number line. Make a number line with the interval endpoints. Okay? That would be the 0 and the 5. And whenever v of t equals 0. So you want to have a number line right here, 0 and 5, 1 and 4. They don't have to be in perfect order or spacing. So just representing. So we use this to guide us. This is our regions we're looking at, and I need to know when the velocity is less than 0 to indicate moving to the left. So what we do is we use this number line in these regions, and we test the velocity equation right here to see if I'm going to get a positive or negative value for the velocity in these regions. So we want to test the regions. Test each region for when the velocity is greater than 0 or when it is less than 0. Because here's where it's 0. It's 0 at 1 and 4. So you just plug in some numbers in here. You plug in a number between 0 and 1 into this thing over here. If I take a half and I plug that in there, this is going to make a negative number. This will be a negative number, and negative times a negative is positive. I don't care what the numbers are. I just want to know sign. Give me a number between 1 and 4. Let's take 2. If I plug in 2, I'll be negative. If I plug in 2, it will be positive, which means that will be negative. Plug in a number between 4 and 5. I don't know, 4 and a half. That'll be positive. That'll be positive. That'll be positive. So the only region where the velocity is less than 0 is between 1 and 4. So there's my answer. The particle is moving left on the interval 1 to 4 because, and always give me a because, why? The velocity is less than 0 on this interval. That is how you need to express that answer right there. Always tell me why. Okay? And the last one here is C. And in C, we're asked to find at t equals 3, is the particle speeding up or slowing down? Justify your answer. Okay? So what I need to find for that one, remember, is I need to know the velocity, which I have all that, and I need to know the acceleration, which means I need to find A of t. A of t, which is the derivative of the velocity function, I can just take the derivative of this thing right here, and I get my, which is, if you want to, you can say, okay, well, this is also the second derivative of the position, and I get 2t minus 5. Okay? And so what I need to know is I need to know what happens at t equals 3. And since I know this is that equation, at t equals 3, which is in here, I know that the velocity at 3 is going to be less than 0. Actually, you know what? Let's just plug it in to be sure. We already know it, but let's just say I didn't do this part already. So let's plug 3 into our velocity function, which is going to be 3 squared minus 5 times 3 plus 4. And we see that that number is going to be equal to negative 2, which is less than 0. And what is the acceleration then at 3? Well, it's 2 times 3 minus 5, okay, which is equal to 1, which is greater than 0. So they are of different sign. Based off of that, I can conclude the particle is slowing down at t equals 3 because A of 3 and V of 3 are different signs. And there you go. And so that's how you would answer a question like that. Please remember how to express your answers and what to show in your answers, please, because that is very important. All right, I have another example right here. This one's you giving information in a table setting, so let's see what this one is asking us to do. He is competing in a 50-minute training run on a straight path to prepare her for an upcoming marathon. Her velocity is given by the differential functions v of t, where v of t is measured in meters per minute and t is measured in minutes. Selected values of this velocity, this equation, are given in this table right here. Estimate Tina's acceleration at t equals 10. Indicate proper units. Let's start with that question. Okay. Acceleration is the derivative of this velocity, but it says estimated. Well, it's estimated because I can't actually take the derivative of v of t because I don't know v of t, which is why I can't find the acceleration at 10. But I can estimate it because remember, the acceleration is the derivative of this, and an estimate for the derivative is the secant slope. Okay, so what we want to do is find out where 10 resides, and then we want to find values of t around 10. You can also include 10 as one of the endpoints if you have 10 given. So 15 and 5 is where 10 resides, in between that. So this is the interval I'm going to use right there. And okay, so my a of 10 is approximately the secant slope, which is the velocity of 15 minus the velocity of 5, and then the time 15 minus 5. This is your difference quotient. Do you remember doing this? F of b minus f of a over b minus a. Using that interval right there, we plug our numbers in. You must write that down. You must write that statement down, and then you can plug numbers into it. So this is 220 minus 170, and this down here is 10, because I already know that. And then I can get an answer here. If you work this all out, you should get something in the neighborhood of 5. And then what units am I going to have? Well, the units of V are meters per minute. T is in minutes, so it is the units of the function above, which is this. So it's meters per minute, and then per minute, the units of time. Okay, you can also put it as meters per minute squared is also acceptable. That is the acceleration. Okay, must Tina have switched directions in any of the subintervals indicated by the table? Explain why or why not. Okay, well, directions we talked about already are based off of positive and negative. It is moving to the left or down, right or up when the velocity is from positive or negative. Well, it switched from positive to negative. To determine when I switch directions, I first have to stop. You cannot change a direction without first stopping. Okay, so that gives us indication of what we can do. So, little side note here. So whenever the velocity changes sign, the particle changes direction. Okay, so we want to find out when that happens. So when did the velocity change sign? Here's my velocity. 0 is not a sign. So we have what? Positive, positive, oh, negative, sign change. Negative, negative, positive, that was a sign change. Okay, so what does that tell me? So the question is, must Tina have switched directions in any of the subintervals indicated by the table? Explain why or why not. Answer, yes. And on the intervals 15 to 32, this interval, and that interval, 40 to 50. Why? Because V of t changes sign. There you go. That is the answer in your reason. Okay? And I have one more example. This one is dealing with a graph was given. So a particle moves along the x-axis with a velocity given by the differential function v of t between 0 and 6. The graph of the velocity is shown. This is the velocity graph. The velocity is 0 when t is 0, when t is 3, and when t is 5. And the graph has a horizontal tangents at 1 and at 4. Okay? Part A. For t between 5 and 6, is this particle speeding up or slowing down? Explain. So again, I don't have a function. I don't have a table. I only have a picture. So how can I do this answer and figure this out? Well, let's break this down. A particle's speed is determined by the sign of the velocity function and the sign of the acceleration function. If they are the same, then it is speeding up. If they are different, then it's slowing down. So the point of is in this interval between 5 and 6, so in here. So what is the relationship between these? Okay, so the relationship between the velocity, which is what I see, when I look at a graph, anytime it is above the x-axis, then the y values are positive. Anytime it is below the x-axis, then the y values are negative. So the velocity on the interval between 5 and 6 is below the x-axis, so therefore it is negative here. But what about the acceleration? Remember, the acceleration is the derivative of the velocity. And the derivative are basically little tiny tangent lines to the curve. So if I take any point in here between 5 and 6 on this curve, and I draw the tangent line there, I'm going to get a line that is negative slope, which means the acceleration is also negative. And so my answer is going to be this. On the interval, okay, where t is between 5 and 6, I can use the interval notation also. The velocity of t is less than 0, and the acceleration of t is less than 0. So the particle is speeding up. Because v of t and a of t have the same sign. Okay? What about part B? During what intervals, if any, is the acceleration of the particle positive? Justify your answer. Okay? So, again, the acceleration is pretty much the derivative of every point in here. So at any point I look at, I can put a dot here and look at a tangent line, and the slope of that line will determine if the acceleration is positive or negative. This is why they gave you this concept here, is you have horizontal tangents at 1 and 4. So at 1, we have a horizontal tangent. At 4, we have a horizontal tangent, meaning the acceleration is 0 there. Okay? The acceleration is 0 here and here. So what is it here? If I pick a point between this interval right there and I draw a tangent line, that line is going to be negative. If I pick a point in here, like 3, well, and I draw a tangent line there, that slope is going to be positive. And then anywhere over here, we've already done this one, but you can do anywhere here, and the slope will be negative. So I know between 0 and 1, the acceleration is negative. Between 1 and 4, the acceleration is positive. And between 4 and 6, the acceleration is negative because of the tangent line slopes. So, during what intervals, if any, is the acceleration of the particle positive? There you go. The acceleration, which is the derivative of the velocity function, is greater than 0, positive, on the interval 1 is less than t is less than 4. Okay? And it's, I kind of wrote, here's the because. On the interval, because it's positive there. And that's how you can give your answer here. Okay? So that concludes this video. And let me show you the notes real quickly, and you can pause at each page so you can copy them down. Here we go. This is page 1. Here's page 1 still. Page 2. You can pause there. Okay. Here's the third page. And here's the last examples with my little side notes. And then the last example. Okay, so make sure you ask any questions in class, and that concludes this video.